Okay, so now continuing where we left off with hypothesis testing and for 7.2, we're going to be doing hypothesis testing for the population mean when sigma is known. So if the population standard deviation sigma is known, that means we use a z-test, which means we're going to be using the z-table. So we have to remember this definition here for z, for our z-score. Z equals x bar minus mu over sigma divided by the square root of n. So the steps here for hypothesis testing for the z-test are going to be as follows. First, we have to verify that sigma is known. Once we know that we have sigma, that's how we know we're doing a z-test. Next, we have to state the claim and identify the null hypothesis and the alternative hypothesis. So one of them is going to be given to us in the problem. We have to determine if it's the null or the alternative, and then we have to figure out the other one. Then we just have to identify the level of significance, alpha, which will be given to us. And then we have to calculate that z-score, which we call the standardized test statistic now. And now from section 7.1, we have to determine if the test is left-tailed, right-tailed, or two-tailed. So once again, that's based on the alternative. And next we have to find the p-value, which is the area that corresponds to z, using the z-table based on if it's left-tailed, right-tailed, or two-tailed. So I'll come back to that in a second. And then we have to compare that p-value with alpha, and that'll tell us whether or not we reject or fail to reject the null. And then we want a concluding statement in terms of the original claim, in terms of the actual problem. Okay, so coming back to kind of steps 5 and 6 here. If we have a left-tailed test, that means the p-value that we're finding is the area to the left of z from step 4. If we have a right-tailed test, then the p-value is going to be the area to the right of z, which, remember, area to the right on the z-table is 1 minus the area to the left. And lastly, if we have a two-tailed, that one is when the p-value is the area to the left of negative z plus the area to the right of positive z, which we can just find one of them since they're the same. So it's going to be 2 times the area to the left of negative z. Technically, it could be 2 times the area to the right of positive z also, but since the table tells us the area to the left, it's easier just to find that one. Okay, and once again, I'm referring to the values from the z-table here. Okay, so let's do a couple examples here. We'll do kind of one of each setup example. So a pit crew claims that its mean pit stop time is less than 13 seconds. A random sample of 32 pit stop times has a sample mean of 12.9 seconds, which notice is less than 13. Assume the population standard deviation is 0.19 seconds. We want to know if there's enough evidence to support that original claim at a significance level of 0.01, so alpha is 0.01. Okay, so what I'm going to do here is first just recognize that the claim up here is the mean is less than 13, so I'm just going to write that right here, mu less than 13. And while I'm at it, I'm also just going to write down the givens. So we have 32 pit stop times. That's going to be our sample size. And it has a sample mean of 12.9. So x bar is 12.9. And we have a standard deviation of the population, which is 0.19. And we're given alpha is 0.01. Okay, so setting this up now, the first thing we have to do is verify that we have a sigma. So we do have the population standard deviation. So that means we are doing a z-test. So obviously we're doing a z-test because we haven't gone over the t-test yet, but that is important. So next it's going to be setting up the hypotheses. So we're going to have the null and the alternative. So from the original problem, we had mu less than 13. That has to be the alternative because there's no equality. So that's the claim. So if that's the alternative, then the null is the opposite, or the complement. So that would be mu greater than or equal to 13. Okay, so the type of test we're going to be doing here is going to be a left-tailed test because of the alternative. The alternative is less than, so it's left-tailed. So it's going to be the area to the left of the z-score. So next we have to calculate the z-score. So that's going to be our usual formula. Z equals x bar minus mu over sigma divided by the square root of n. So we have all these numbers, so we're going to plug them in. So it's going to be 12.9 minus 13. So the mu that we're plugging in here is the hypothesized mean in the question, which is 13. And divided by 0.19 over the square root of 32. So plugging everything in, we get z equals negative 2.98. Okay, so step 4 here is going to be finding the p-value. So the p-value is going to be the area to the left, because it's a left-tailed test, to the left of the z-score. So going up here to the curve, we're on the z-curve here, the standard normal curve. We have a z-score of negative 2.98, and we are trying to find this area to the left of it. And that's going to be the p-value. Okay, so the area to the left of z equals negative 2.98, that's going to be on the table. So that's directly on the z table, and that gives us a p-value of 0.0014. Okay, so that's our p-value. Now we have to come up with a conclusion by comparing it to alpha. So I just sort of condensed the steps from the first page here into 5. So comparing this to alpha, we have alpha was 0.01. We have 0.0014. So that means p is less than or equal to alpha, because remember, it's either less than or equal to it or it's greater than it. We know it's less than or equal to it because it was 0.0014 for the p-value, which is less than 0.01. So when that happens, that means it's a low probability of this outcome occurring. And since we start with assuming the null is true, a low probability of it happening means it's safe to say that we can reject it. So if we can reject the null, that means we can accept the alternative. So now we want to write this in terms of the original problem. So what we could say, since the claim is the alternative, and we're accepting the alternative now, we could say there is enough evidence at the 1% level of significance. So I like to bring into play the alpha because that is really important. There is enough evidence at the 1% level of significance. We are accepting the alternative, so we are accepting the claim. So we can say there's enough evidence to support the claim. And now we just have to say the claim in terms of the problem to support the claim that the mean pit stop time is less than 13 seconds. Okay, so you need that conclusion in terms of the problem so it actually makes sense for what we're doing. So let's do 2 more here. So homeowners claim that the mean speed of cars traveling on their street is greater than 35 miles per hour. a random sample of 100 cars has a mean speed of 36 miles per hour. So notice that is greater than the 35 from the claim. Assume the population standard deviation is 4 miles per hour. Is there enough evidence to support the claim at alpha equals 0.05? Okay, so running through our givens here, the claim is that the mean is greater than 35. So that's mu greater than 35. We should already know that's going to be alternative because there's no equality. And let's write down our other givens. We have a sample size of 100 cars. We have a sample mean of their speeds is 36. We have the population standard deviation is 4. And the significance level is 0.05. Okay, so let's set up these. Well, before we set up the hypotheses, let's verify that we have sigma. So we know we're doing a z-test. So we do have the population standard deviation. So that's how we know we're doing the z-test. So next, let's set up these hypotheses. So setting these up, we're going to have the null and the alternative. And we already said that mu greater than 35, the claim here has to be the alternative because there is no equality. So if that's the alternative, then the null has to be less than or equal to 35. And we know that this is going to be a right-tailed test because the alternative says greater than. So we know we're going to be finding an area to the right of the z-score, and that's going to be our p-value. So now let's calculate that z-score. So we have our usual formula. We're going to plug in our values for our givens here. It's going to be 36 minus 35 over 4 divided by the square root of 100. So calculating that, that's going to give us a z-score of 2.5. So if that's our z-score of 2.5, we know it's going to be the area to the right of 2.5 because this is a right-tailed test. So this area to the right is going to be our p-value, and then we're going to compare that to alpha. Okay, so finding the p-value now. So for the p-value, since we're looking for the area to the right of that z-score is going to be 1 minus the area to the left. So 1 minus the value from the table. The value from the table is 0.9938. So this is going to give us 0.0062. So that is our p-value. P is 0.0062. Okay, and now we're going to do the conclusion by comparing that with alpha. So our p-value here is less than or equal to alpha again, because our p-value was 0.0062, which is less than or equal to 0.05. So since that's the case, once again, we reject the null. And whenever we reject the null, we accept the alternative. So now we need to say this in words in terms of the problem here. So once again, we're accepting the alternative. The alternative here was the claim. So if we're accepting the alternative that is the claim, we can set it up just like we did in the last one and say there is enough evidence at the 5% level of significance to support the claim. And the claim is that the mean speed of cars is greater than 35 miles per hour. So it's saying that they would be most likely correct with that claim at a 5% level of significance at a 5% maximum allowable probability of error. Okay, let's do one more with the last kind of setup here. So a certain study claims that the mean cost of surgery is $21,500. You think the information is incorrect. You randomly select 25 patients and find the mean cost is $20,695 and assume that the population standard deviation is $2,250. We want to know, is there enough evidence to reject the claim at a significance level of 0.05? Okay, so once again, we have the claim is that the mean is $21,500. So this is going to be an equal to one. So this is going to be mu equals 21,500. So automatically we should be thinking that this is going to be the null because there is some sort of equality here. And let's write down the other givens here. So we have a sample size of 25 patients. We have a sample mean of $20,695. We have a population standard deviation of 2,250 and a significance level of 0.05. Okay, so starting this off, sigma is known, population standard deviation is known, so we know we're doing this z-test. And next, for setting up these hypotheses, we know from the claim mu equals 21,500. We know that that is going to be our null. And I'm just going to write down that that is the claim. And then write down the alternative. So if the null says equal to, that means the alternative says not equal to. And that means we know we're going to be doing a two-tailed test. So we're going to have to find z next, and then we're going to do the area to the left of negative z and the area to the right of positive z for the p-value. So plugging in the values into our formula, we have the sample mean was 20,695. The hypothesized mean was 21,500. And the standard deviation 2,250 divided by the square root of 25, that's going to give us z equals negative 1.79. Okay, so next for finding the p-value. So for finding the p-value here, what we have to do is let's go just shade in what areas we're looking at up here. It's going to be the area to the left of negative z and the area to the right of positive z. So that's going to be the area to the left of negative 1.79 and the area to the right of positive 1.79. So we can shade in those regions. That's going to be this region right here and this region right here. So both of these are going to be 1/2 of the p-value. So together it's going to be a full p-value. Okay, and then instead of having to find both of those separately, all we have to do is 2 times, since it's symmetric, those areas are equal. So we have to find one of them and multiply it by 2. So it's going to be 2 times the area left of z equals negative 1.79. So that's going to be equal to 2 times the area to the left of negative 1.79 from the table is 0.0367. So we multiply those together and we get 0.0734. So that is our p-value. P is 0.0734. So now we're going to compare that for alpha for our conclusion. So in this case, our p-value is actually greater than alpha because 0.0734 is greater than alpha, which was 0.05. So when this happens, what that means is we fail to reject the null hypothesis. Okay, so remember, failing to reject it does not mean we can accept it. It just means we failed to prove it wrong, and that is it. So for this one, if we fail to reject, what we can say is there is not enough evidence at the 5% level of significance to reject the claim that the mean cost of surgery is $21,500. So we failed to reject the null, so that means there's not enough evidence at that significance level to reject the null because the claim was the null. So there's not enough evidence to reject the claim, and then I just repeated the claim in terms of the original problem, that the mean cost of surgery is $21,500. Okay, so if we fail to reject the null, we can start by saying there's not enough evidence, and if we do reject the null, we typically start by saying there is enough evidence. Okay, so essentially we just could not prove the claim wrong. We couldn't prove the claim wrong at this level of significance. Okay, so that is it for the z-test in chapter 7.3. In chapter 7.3, we'll be doing it with the t-test.